Okay, welcome to the first of three, hopefully short, little lectures on atomic and nuclear physics. There are basically three types of problems they can ask. Energy level problems, which we'll do first. Then there are radioactive decay problems, which we'll do second. And then the last one is the photoelectric effect, which probably the trickiest of the three, just because there's so many different ways they can ask the question. But the first two are pretty straightforward. So let's get going. Okay, you know that you're made of atoms, that everything is made of atoms. Um, there's a cycle to everything, so you can do whatever you want, but the pieces of an atom remain the same. And you see down here at the bottom, it says taking something in, allowing something out, but there's a conservation that goes on. So you know the statement, the atom is the building block of all matter, blah, blah, blah. You know about the nucleus. We've gone over this, and I know other classes have as well. You get your protons and your neutrons, and those are called nucleons. And the electron cloud outside of the nucleus, where the electrons are orbiting and always moving. Okay, that's very important. We're going to be using the Bohr model for a lot of this stuff, and even though it's not correct, it's a real easy way to think about it. And then, of course, you know that what makes all these elements different is the simple addition or subtraction of nucleons. So if you have, I don't know, carbon, and you add a couple protons to the nucleus, all of a sudden you have oxygen. Add a couple more, you get neon, and it just keeps going. And that's really the only difference between everything. Now here's the first new part. We're going to talk about levels, energy levels. So what I want you to do is, you've got a ladder right there. Try to imagine a ladder. N equals 1, and once again is just a variable, stands for number, is called the ground state. Maybe you've heard that in the movie before, ground state. It is the lowest energy level that an electron can occupy as it orbits a nucleus. N equals 1, so it can't occupy a 0 energy level because they always have to be moving. And 0 energy means you're not moving. So N equals 1 is the ground state. In order to reach N equals 2, the first excited state, you have to insert energy into this atom. And the electron has to absorb this energy, and therefore it can jump up to a higher energy level. So if you want to think about it like maybe a carousel or something, if you stand right in the middle of a carousel, you don't have to exert any energy because you're right in the middle. There's no centripetal force because your radius is 0. But if you take a step farther to the outside, well, now you got to hold on a little bit. If you want to take a step farther outside, you got to hold on more. And if you want to go all the way to the edge, you've got to hold on really, really tight. So the farther out you get from the center, the more energy you need to maintain that orbit. Same deal here. The amount of energy levels really doesn't matter. There can be a lot more than 5. Normally, you're only going to deal with maybe 1, 2, and 3. I can't remember a problem that ever went past 3, so don't worry about that. So if an atom absorbs energy, the electron jumps up to a higher energy level, and if that electron emits that energy, it falls back down to the ground state. So here are these energy levels. So that means all the time these atoms have energy coming in from light, for instance, and energy going back out. It's the only reason you can see things is because they emit radiation in the form of light. I mean, if it didn't emit any light, you couldn't see anything. But some really interesting stuff goes on right here. First off, you're going to hear the word photon a lot. A photon is essentially a packet of light. Light travels in specific quanta, and it just means quantum, just like quantum mechanics. It means a discrete amount. If you want to think of it as a single wave, whatever you want to think about it as, a sweet and low packet, whatever you want to think of it as. But that's what a photon is. It's basically light, a piece of light. So you see over here, if an electron is excited, that means energy is absorbed, and therefore photon is absorbed. So light, which is energy, it's all energy because that's why it travels at the speed of light. If it had mass, it couldn't. So this photon strikes an electron, and the electron absorbs this energy. Also, if an electron releases energy, if it's in maybe n equals 3 and it drops to n equals 2 or even n equals 1, it has to lose energy in order to make that jump. Well, that is emitted in the form of light. A photon will create out of the electron, will just boom, all of a sudden there's a photon and the electron drops down. Now, these quantum of light, these quanta, these packets, they're very definite. For instance, an electron will never jump to an n equals 1.6 energy level. It just doesn't happen because there isn't one. Just like rungs of a ladder, you can't put your foot halfway between two rungs and take a smaller step up. You have to put your foot on each rung. So these leaps are called quantum leaps because they're very discrete, they're very definite, and it's jumping between levels. And there was an old TV show called Quantum Leap. I'm sure you'll see it one day. Now this photon, this light, is emitted. How much energy it has determines what kind of emission we're talking here. A very low energy photon emission would be radio. A very, very high energy emission would be gamma. So the bigger the jump, the more energy that needs to either be absorbed or released. And I guess the best example of this would be things that glow in the dark. If you've ever wondered, probably not. But things that glow in the dark, what you do is you have to leave them out in the light, right? You have to leave them in sunlight. And by leaving them in the sunlight, all these electrons are just absorbing photons. All this energy from the sun is getting sucked up by these atoms. And they jump energy levels. These electrons all jump energy levels because they're absorbing this energy. Well, when you stop and take the thing out and put it in the dark, those photons are now losing their excited state. They're jumping back down to ground state. And in order to jump down, they have to emit a photon. Well, the photon that's emitted is light. And that's why things can glow in the dark. So, real quick, I'm actually going to write something. There is something called an electron volt. Now, don't worry, you don't have to learn a new concept. An electron volt is just a unit, and here's the symbol for it, by the way. Is just a unit for energy, which is in joules, remember? Now this energy in joules, since we're dealing with atoms here, we're not dealing with 50 joules of energy, or 10,000 joules of energy, or even like 0.5 joules of energy. We're dealing with like 10 to the negative 15th joules of energy. And after a while, if you're a scientist and you have to keep saying 10 to the negative, 10 to the negative, 10 to the negative, you get tired of it. So what you have to do, or what they do, and you'll see it on the next slide, is instead of using the unit of joules, they just use the unit of electron volt. And here's how you do it. You take the energy in joules, and all you do is you divide it by, hopefully you recognize this number, 1.6 times 10 to the negative 19th, which is the fundamental charge, the charge of one single electron. And now, instead of having to say, oh, this one had 1.25 times 10 to the negative 17th joules of energy, we can say, oh, this thing had 1,200 electron volts, which is just a lot easier. Okay, so we can calculate the energy of the released or absorbed photon provided we know enough about the initial and final state of the electron that jumps energy levels. So as long as we know what energy level it was and where it is going in terms of what energy level it ends at, if we know that, we can calculate everything about this wave that's going to happen, and we do so using this equation right here. E is equal to h times f. H is a constant that is going to be given to you, so don't worry. It is called Planck's constant. And the value for Planck's constant is 6.63 times 10 to the negative 34th. And once again, you don't have to memorize that. It's going to be given to you. Now, we remember from waves that we did V is equal to lambda. Well, if I look at this, you can see that if I'm dealing with light, then this V becomes a C for the constant speed of light, 3 times 10 to the 8th. And frequency is equal to speed of light over wavelength. So all they did is they substituted in. So those two equations are also given. They're on your equation sheet. But if you look at it, it's two constants, h and c, And one cool thing they do for you is on the front of your equation packet, they actually give you h times c, so you don't have to multiply them together all the time. They give it to you since it's so commonly used. So if you know the energy beforehand, the energy change, this is a constant, therefore you can calculate the wavelength of light. It might even be a color. Now, you'll see energy level diagrams, and all energy level diagrams are what you see right here. These energy level diagrams, if you look at it, they're just bars. You notice the biggest jump is from N1 to N2, and the jumps will get smaller as you go up. Okay? So absorption means you start here at n equals 1, and you jump up to n equals 2. So this is absorption, when it increases its energy level. Now, an emission is when it drops. And remember, it can drop 1 energy level, it can drop 2 energy levels, it can drop 50 if you want. Normally, it's 1, 2, or 3. But this diagram is actually, I mean, this is the real types of diagrams they use to document the absorption and emission of energy from an atom. And you see down here at the bottom, it is very important to understand that these transitions do not have to occur as a single jump. Maybe this atom will jump, this electron, sorry, will jump from here to here, and then it'll jump from here to here. If it does that, there's more than one photon that is emitted, so you can't just ignore the steps that you use to get there. You have to look at each individual piece. In a real quick example, here you see the symbol for electron volts. A real quick example, it says an electron releases energy as it moves back to its ground state position. As a result, photons are emitted. Calculate the possible wavelengths of the emitted photons. So here in your, and I apologize for the quality, you can see that this energy level is 3 electron volts, which means in order to get from the ground level to the n equals 2 level, in order to get from here to here, that electron needs to absorb exactly 3 electron volts worth of energy. Exactly. If it only absorbs 2, it won't get there. Okay, and if it wants to go here, it has to absorb exactly 1 electron volt worth of energy. Now, in real life, the numbers are usually not this convenient, but it's a good example. So, it says, calculate the possible emitted wavelengths. And your equation is, from before, and if you solve for lambda, so in order to get from 3 electron volts up here to ground state, it has to lose 3 electron volts. And there's 2 possible ways to do that. There's only 2 possible ways to do that. The first way is to jump all the way down. Bam, lose 3 electron volts. And if you look at your equation here, that would be the energy you have to lose. It's never a dull moment. Okay, so there's only 2 possible ways for this this electron to get back down to ground state. It can jump all at once and lose 3 electron volts, okay? Or it can jump once and then twice, losing 2 the first time and 1 the second. And if it does that, then you have to calculate each individual electron energy change. Now, where does this 1240 eV come from? Remember, I told you they give you Planck's constant. They give you hc. Okay, and hc just happens to be 1240 electron volt nanometers. Don't worry about the units. Just worry about the 1240. And you'll notice it's the same in every single one of these because it's a constant. H times c is a constant. And what happens is when you plug this thing in, the electron volts cancel out, which is why it's important to put your energy in. And you see that you get 413 nanometers for that's if it makes the big jump. If it makes the small jump, it will emit a 620 nanometer and a 1240 nanometer wave. Okay? And what that means is this particular sample will release 3 different wavelengths, with 2 being in the visible range, red and violet. Red is the 413. Violet, or sorry, the other way around. The 413 is your violet, and the 620 is your red. and one would be far outside. We're only in the 700-800 at the most, so this is well outside our visible spectrum, but it's still energy that is emitted. Some examples of this: spectroscopy. Say that 10 times fast. If you burn something, it burns a certain color, and elements are no different. If you want to know how we can look at a star and say, oh, this star is made up of 98% hydrogen and 1.6% helium, or whatever it is, it's from spectroscopy. Every single element, if you look at it with a special glass, remember when I gave you the polarizers and everything looked like rainbows? If you get a very, I guess, narrow range one of those, and you look at something like, for instance, oxygen colored light, it will make marks in the spectrum. You can see this is mercury, and you can see mercury makes lines here, 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 a whole bunch here, here, and there's one right there maybe. No other element makes lines like that. So if we look at something, even if it's billions of miles away, and it looks like that, we know that it's got mercury in it. Now, since stars are usually made of several things, what you do is you look at it and the computer kind of matches things out. So it says, oh, this is mercury, lithium, and cadmium, and strontium, and calcium, and sodium, and everything like that. And last slide, these emission line spectra, they show you what wavelengths these electrons are emitting. Because remember, the energy level diagram, it's a very specific amount of energy to jump. Therefore, it's always going to release the same exact wavelength of photon. So we know that when we see this particular emission line spectra right here, we know when we see that, we know that that atom has a very specific energy level size, and whenever an electron jumps, it will release exactly that much energy. And that much energy releases exactly that color wave, or that size wave. So we know that that's sodium, for instance. Okay, the next thing we are going to go over, sorry, this one ran a little long. The next one we're going to go over is radioactivity. This one is way shorter. Hopefully you can try to keep it under 5 minutes. See you then.